In our last lesson, we were looking at low frequency light. Today we want to look at visible light. Same ideas we talked about before with wavelength and frequency and how different frequencies and different wavelengths have different effects. But this time, let's focus on what we can see. So I want to remind you that the visible spectrum runs from red on one end to violet on the other. The red end is low frequency, and the violet end is high frequency. Remember, high frequency means small wavelength, and remember, a low frequency will mean a larger wavelength. If you need to find the wavelengths, all you have to do is use our formula, where you use the speed of light as your velocity. The thing I'd like to make sure you know, and you probably have heard this at least once before in your life, but when you talk about white light is actually composed of all of the different visible colors of the spectrum. So if you take white light and shine it through a prism, out will come all the colors from red to violet. The first person who ever noted this, because after all, people had seen this since earliest days with rainbows and other effects, is that white light can be broken up into the colors, was Isaac Newton. He went one step farther and realized that he could break the white light up into colors and then send it through another prism and turn it back into white light. So he's the first one to recognize that white light was not a color in and of itself, but was a combination of all of the other colors, and that we could combine the colors together to get white light. We now know that there are actually three colors that are special, and these are called the primary colors. These colors are special because using different amounts of these three primary colors can yield all the different colors that the human eye can see. So when we look at these primary colors, they are red, they are green, and they are blue. So red, green, and blue are the three primary colors of light. You should know the combinations. So if we have 100% red and 100% green, that gives us yellow. When we have green and blue, we get cyan. And when we get red and blue, that gives us magenta. When we put all three of the primary colors together, just like Newton realized, we get white light. If we have none of the primary colors, then that would appear to be black. So this color combination graphic is what you want to make sure you commit to memory. You want to make sure you know how 100% red, green, and blue combine together to give us those other colors. These three colors, the yellow, the cyan, and the magenta, would be our secondary colors. A few days ago, you played around with an activity where you combined different amounts of these primary colors together, and hopefully you showed that you could create all kinds of different colors and different shades of different colors. So for instance, with this one, 100% red, no green, no blue, obviously we have red. But as we add more green to it, you'll notice that your red turns into an orange. And then if I start adding some blue, we get more of a salmon colored color. If we take away some of the red, and we have 50% red, blue, and green, we get gray. And again, there's an infinite number almost of combinations we can come up with, and each one will lead to a slightly different shade of one of our colors, or some color that doesn't appear in the rainbow altogether. All right? This technology is used for many of you in the lights that you might have around your room that you can change to any color you want using your smartphone and one of the apps on it. The way it works is it will actually be a light that is composed of three separate components: a green, a red, and a blue. And by adjusting the amounts of each of those primary colors, you can turn your lights into any color that you would like. So here are some examples of some colors, and hopefully you would be able to understand how you would create them using lights. So if I want red light, green light, or blue light, obviously I just use one of the primary colors and I turn off the other primary colors totally. If I want yellow, I would do red and green at 100%. If I want magenta, I would do red and blue, both at 100%, and I would get magenta. Cyan, I would use 100% green and 100% blue. When I want white, I combine 100, 100, and 100, and I would get my light looking white. If I want black, I have 0, 0, 0, and I would get the black. When I want gray, it's 50, 50, 50. And you saw orange is composed of 100% red, 50% green, and 0% blue. So you played around with this and you found these different combinations just the other day. I want to now take a step back and make sure you understand that everything we talked about was adding light to light. Many times we're going to have objects that instead of being light are actually taking away light. So when you have things like this red notebook, this is not producing its own color. This is reflecting light and taking some of the colors away from it. When I have white, all of the colors are reflecting off, the red, the green, and the blue. When I have red, only the red is reflecting off and the green and the blue are being absorbed. So this is known as subtractive colors. So if you have a black shirt, that black shirt would be absorbing red, green, and blue, leaving no colors to reflect off. If you have a white shirt, this would be reflecting 100% red, 100% blue, and 100% green to make white. Then when you see the rainbow, the area that's red would obviously be reflecting red. It would obviously be absorbing green and blue. When it's orange, the orange would be 100% of the red light reflects and 50% of the green reflects and none of the blue reflects. All of the blue would be absorbed. And you can go through every single one of those different colors and figure out what is being absorbed and what is being reflected. Okay, we're going to look at our same dots that we had before, and this time these are not lights, but these are things that are reflecting light. So if we take a look at red, this would be absorbing blue and green, reflecting red. Reflects green, which means it absorbs blue and red. White would be reflecting all of them. Black would be absorbing all of them. When we look at gray, gray would be absorbing 50% of all of the colors that are reaching it and reflecting 50% of the red, the green, and the blue. When you have cyan, okay, cyan we saw was a combination of blue and green, which means if you have something that's cyan, it is absorbing red. There is no red being reflected from something that looks cyan. When something looks magenta, it is absorbing green, leaving behind red and blue. And finally, if it's yellow, the yellow would be absorbing the blue light and reflecting red and green. So it's a little tricky. When you're trying to determine when you mix colors together, what are you going to get? You have to ask, am I mixing colors or are my objects removing colors? So for instance, when you buy ink for your printer, or paints, or crayons, or dyes, they do not produce their own light. So when you mix the dyes or paints or inks together, instead of using our original color combinations, we would use this for subtractive colors. Now our primary colors are cyan, yellow, and magenta, and you can see how they combine together. Now when we combine all of them together, we get black. White is now none of them. Okay, so everything has reversed. Now if we take yellow and cyan, we get green. Yellow and magenta, we get red. Magenta and cyan, we get blue. So again, adding lights versus adding pigments, you do everything exactly the opposite. With pigments, you are absorbing colors and reflecting others. So if I have a yellow folder, think about what makes yellow. We go back to our thing here, and we remember yellow is red and green. So if I have a yellow folder, it is absorbing all the blue light. It's reflecting everything else. If I have a red filter, that's allowing red to get through. So that's absorbing blue and green. I know it's a little bit confusing, so if you take nothing away from today's lesson other than these ideas, I'll be very happy. And that is adding lights together and adding dyes and pigments together are the exact opposite process. When you add lights together, red and green and blue make white, and when you add dyes together, your three primary colors will give you black. All right, so hopefully you at least picked up on some of these ideas and that you know the primary colors for light are red, green, and blue, and the primary colors for inks and dyes are cyan, yellow, and magenta.